So the interpretation of this is, again, holding x2 fixed, how much output do we get for each unit of input x1? So that's average physical product of good 1. Graphically, what that looks like is we can take a point from the origin, and if we're interested in the average physical product of good 1, say at this point, then the average physical product of good 1 is just equal to the slope of this ray that goes to this point on the total physical product curve. And geometrically, you can kind of see that this is just equal to, this point is just equal to this point y divided by this point x1. So that's this, such that the rise over the run is equal to the average physical product. At a point, yes. So these are all functions. So the average physical product is a function of x1. Okay, so to go with that, we have also the marginal physical product, which I already sort of had a picture of and waved my hands a little bit. The marginal physical product is the rate at which output changes as we increase vary 1, but it's the marginal rate. So it's think of a small change in production, and it's going to the answer to the question of what's the marginal physical product is going to be related to the slope of. I should have drawn this better. Let me pick a different point here. It's going to be related to the slope of the total physical product. So the marginal physical product of good 1 is just equal to df dx1. It's just a partial derivative. It's the slope of the total physical product thing held at x1. And of course, when we take partial derivatives, we're already holding all the other inputs fixed. So we don't even need that notation. All right. Questions about these? Okay. Let me change gears. Oh, no, hold on. I'll give you another important example. Hold on. So we're going to talk a lot about sort of stylized mathematical versions of production functions over the next few weeks. We've also talked our way through some examples of production functions like peanut butter and jelly sandwich production and so on. I'd like to introduce an artifact that sort of combines these two things. So this is this was an object which was made by a former member of the faculty of the then Department of Agricultural Economics here at Berkeley, William Bressler, and he signed it here. He did this in February 1952. This is a three-dimensional graph of a corn production function. And the inputs that Professor Bressler used for his corn production function were two. He held land fixed. And it was one of the experimental plots we have over here, west of campus, I believe. So he held land fixed. And he had, growing corn. What he varied was the amount of water and the amount of fertilizer that was applied to the growing corn plants. Okay, so here's the production function. Let me write it down for you. So he got data, from these experimental plots and posited a quadratic production function. So there's three things going on here. One thing is the height of this thing. This is the output. So y is corn output in his example, and measured in bushels, I believe. This input in this direction is one of the two inputs. This is water. So you can see, as you want to go this way, as you increase the amount of water, you get an increase in the amount of corn. So he had x1 equal to water. And then finally, in this direction, this is fertilizer. So you add fertilizer, you get more corn. Now, notice something that's different between this. So we increase water, we get more corn. What's different as we increase fertilizer? Yeah, so it's quadratic. This is the quadratic part. We get an increase for a while, and then as you put on too much fertilizer, you get a decrease in output. The fertilizer burns the corn, and you get reduced yield. And so x2 here is fertilizer, nitrogen fertilizer. Anyway, so he collected these data from these experimental plots and did an early example of using econometrics to estimate a production function. So he ran a regression, for those of you who are familiar with that, and here's what he got. He estimated that corn output was equal to 20, I think it was in acres. So 20 bushels per acre plus 6.67 times the amount of water plus 10 times the amount of fertilizer minus 1/2 x2 squared. So this is where the quadratic piece comes from. If you have too much fertilizer, you get a positive impact from fertilizer from this, but at too high a level, the quadratic piece overcomes that, and you get a negative decrease in return. So he estimated, he regressed output on a constant water, fertilizer, quadratic, and fertilizer, estimated these coefficients, and then and he did use a computer to do this, but the computer wasn't capable of producing graphical output, so he built a cardboard model, and here it is. Yes. Yeah, that's so. If you, this is a general point, which is, when you're modeling these things, especially estimating things, you choose sort of a domain you want to do it over. So for sure, if you flooded the field and left it flooded for a couple of weeks, you get zero output. So if you added enough water, that would be decreasing as well. So he was trying to mess around. I mean, he was trying to give advice to farmers in California. So he was interested in varying the amount of water and fertilizer over the kind of ranges that farmers, had experience with and that weren't obviously stupid. So he wasn't flooding the fields. But you're absolutely right. If you did the experiment, so he just wasn't generating data. He didn't have a treatment where you flooded the field or even added a huge amount of water, because in the Central Valley, too much water for corn is never really a problem. Yeah.
If you don't mind, go back to the subway examples. I think these are illustrated this point. Okay, so what about perhaps if the employees, they have all the same inputs, all the same amount of bread, they're 2 employees, they have the same amount of bread, same amount of turkey, roast beef, lettuce, all that, but they have an 8-hour shift. So for the first 6 hours, they're probably more efficient than the last 2 because the fatigue can start to set in. So there's the same impact as the less.
So a general point. A general point here is that as an individual works longer hours, they may be more productive. Maybe less productive. So that's the point Kevin's making. That's a case where I think if you're trying to think about that carefully, you say, well, so if that's right, you should treat the first hour you're working differently from the last hour and treat those as two different kinds of inputs. So if you thought that people were a lot more productive during the first hour they work, you might hire more workers and have them work half-day shifts instead of full-day shifts. So that would be a way to model that. That was an important aspect of production in that example. Okay. All right. So what I wanted to say about this, though, so I don't, those of you in the back aren't going to be able to see this, but Bressler drew, sort of the commodity space, the input commodity space here on the surface of this thing. So he's got, he sort of made graph paper in effect. He also drew some red lines here, and the red lines, if you look at this thing, I'm sure you can't see this very well. The red lines are level. So if this thing's properly situated, they mark out combinations of inputs of water and fertilizer that generate the same level of output. So each red line is the locus of inputs that produces the same level of output. So the red lines here are what we call, well, you've seen something like this before for consumers. What's kind of like this? Yeah, so good, very good. So a lot like in difference curves, where we have a locus of points that produces the same level of utility. This is the locus of inputs that produces the same level of output. We have a different name for these objects. I mean, mathematically, they're very similar to difference curves. In a production context, what we do is we call these isoquants. So I've got another picture drawn a little bit more that looks even more like difference curves. So here I've got two inputs, x1 and x2. I've got different levels of output. Y1, so this is like 1 bushel of corn, 2 bushels of corn, 3 bushels of corn, and so on. This is all from a production function that you probably can't quite read. These particular isoquants are from a production function of y equal to x1 to the 1/3. Is that right? Yeah. And x2 to the 2/3. Okay. And so those pictures are the isoquants. Now, so there's a lot of, mathematically, there's a great deal of similarity between isoquants and indifference curves, but there are also a couple of important differences. So you might be able to guess what a couple of those, or you've seen examples that might allow you to guess what those are. What's one difference in this picture of isoquants from what we usually do with indifference curves? Well, I put labels here. So when we're producing corn, you can go out and measure how many bushels you produced. And so this sort of issue, this kind of messy issue we struggle with about is utility ordinal or cardinal doesn't really come up with the production usually. You've got so many bushels of corn. We don't need to worry about interpersonal comparisons of how much corn we've got. We have an objective measure we can all agree on, which is how many bushels it is, or how many pounds it is, or whatever. So we care in production more for demand. We care a lot about orderings, preference orderings, and orderings of different curves and so on. For production, we care about the actual quantity of stuff you produce. That's what you're going to wind up selling if you're a firm. So this is more analogous to cardinal utility than it is to ordinal utility. So that's one difference. Another difference is illustrated by the isoquants here. Yeah.
Well, I just have a question. If we were to go back to the peanut butter and jelly example.
You guys love that one. Okay.
Well, how did you produce the same amount? Like, if you produce one peanut butter and jelly, you use the same amount of peanut butter and jelly. You can't have way more.
Yeah, I struggle with it. Well, so when I make a peanut butter and jelly sandwich, there's 2 slices of bread, a lot of peanut butter, and a little bit of jelly. And your peanut butter and jelly sandwiches might be different. Now, if we actually produce those things, I think the way to handle that would be to say, well, there's the Liggins style, the Mongo peanut butter sandwich, and there's the the modest peanut butter sandwich. I don't know. They'd be 2 different outputs. So I think would be the way to model that. Okay. All right. So hold on. Let me see. Oh yeah. I was going to say another difference in difference curves. You can maybe see here, or maybe not so well. So let me see what else I have for you. I think. Here we go. Here's a. Let's see how I did. Yeah. So this is the same. This is that function, written a little bit larger so you can see it. So this is Bresler's corn production function. Here's water, here's fertilizer, and here's bushels of corn. Now, instead of in Bresler's case, he drew these isoquants on the surface of the thing. Here are the isoquants too, but I've drawn them in the input space here on the bottom of this thing. Okay, so what do they look like? Perhaps not great, but anyway, here's what the isoquants look like for the Bresler production function. I hope you can see this. So again, this is x1, or water on the horizontal axis, and x2 on the vertical. Okay, so how are these similar? So we've said these are analogous to indifference curves. If I put up this graph when we were talking about indifference curves and said these are indifference curves, what would you have said? You would have objected. Why? You would have said, if these are indifference curves, they're from a consumer whose preferences violate the axiom of non-satiation. All right, very good. And that's right. So what you can see here is what we already observed, which is if you start off, say, with this much water and then you start adding fertilizer, well, you get more output for a while, but eventually, once you get up to here, you wind up getting less. You're going to get less corn as you add more fertilizer. So we see production processes all the time where there's no axiom of non-satiation for production. It's perfectly possible to use too much of some input and get less output as a consequence. Okay. All right. With that, I'm going to stop, but don't move, because I have a favor to ask you. You had a midterm last Thursday. That allowed me to take a sort of opportunity in the middle of the course to evaluate where you're at. I'd like you to take the last 5 minutes and pass around a form to have you evaluate us and the class. So let me do that and ask you to just quickly fill out this midterm evaluation form, if you would. These are anonymous. I'm interested in what you have to say, and I'll take into account what you have to say here as we proceed through the rest of the semester.